Good morning all of you. Today we are going to discuss about very interesting topics, the topics on Navier-Stokes equations. That is what the basic foundations of computational fluid dynamics, and many of the complex fluid flow problems also we can solve it by using Navier-Stokes equations. The derivations part of Navier-Stokes equations, that what today I will cover it. The most of the part what I am covering it is comes from Sinzel-Simbala book, the derivations part. If you are not following the line by line the derivations, I just encourage you to go through the Sinzel-Simbala book. If you look it for vector notations and related to the vectors operations in fluid mechanics, the best course which is available in MIT open courseware which on fluid mechanics you can get it, and also we are going through this FM White book on fluid mechanics. These are three books, you can always refer it to understand the Navier-Stokes equations part. Now, if you go through it, who is Navier and who is Stokes, okay. The way back the French physicist, okay, Claude Louis Navier, okay, so it is almost 200 years back, and also this George Stokes from as a mathematician from England, both have derived the Navier-Stokes equations independently. So, that is what is we got the Navier-Stokes equations because of these two professors from France and the England to derive, one is physicians, another is mathematicians, to derive the combinations of equations which we call Navier-Stokes equations, which they derive independently and they cross verified, and that is the equations today we are going to discuss it. So, I will talk about start from an introductions part. Also, I will talk about revisit Newtonian fluid and non-Newtonian fluid part, which is quite interesting to look at how we can use for this Navier-Stokes equations, and we will talk about the derivations of Navier-Stokes equations for with the assumptions of incompressibles isothermal flow. Then we will be talk about in a two coordinate systems, one is Cartesian coordinate systems, the Navier-Stokes equations and mass conservations, and similar way we can talk about cylindrical coordinate systems, how we can have the Navier-Stokes equations. Now, after that we can look it, we can apply for a example problems with a what would be the appropriate boundary conditions to solve these Navier-Stokes equations. That is what also we will discuss it. Let us go to the next slides. As if you look it from Cauchy equations, what we get it just in vector forms, in vector form, if you remember it, which is the linear momentum equations deriving with the components like rho by rho t, rho v is velocity plus is equal to del dot product of rho v is equal to rho g is a vectors plus we have the del product or divergence of the stress tensors. This is what we have derived as a Cauchy equations, which is a linear momentum equations for a infinitely small control volumes. We have derived the basic equations for as a linear momentum equations for a control volumes which is having infinitely small control volumes. We can derive where sigma I j is a stress tensors. Now, if you look at, if I look at the component wise, before going to these derivations, I just want to look at what is the component wise of this part. If you go back very basic things, the vectors divergence. Okay. If you look at that del and v, the velocity divergence, it is talking about the net volume outflow from a control volume. Okay. So, if you derive a simple equations as find out the velocity divergence, what it says that, what do we understand from that, if you physical interpretations of that is a volume outflow per unit volume, per unit control volume. Okay. So, if you consider a control volume is a unit, then this is what it indicates, the divergence of velocity is indicates how much volume outflow happens is per unit volume. So, we can consider a 0 for a simple cases where we are talking about. So, that is what is indicates the physical interpretations of velocity divergence. The same way, if I just put it the del into rho and to v, what is this is indicating is the mass outflow for a unit control volume. That is what is indicating me. That same way, this for volume outflow per unit volume, if I multiply volume with a rho, the velocity with rho, that is what is mass outflow per unit volume. Same way, if you can just interpret it that the divergence of rho v v, okay, is nothing else is a momentum outflux per unit control volume. So, if I try to interpret this, the physically this part, okay, nothing else, that is what change in momentum. Okay. Here we have a linear momentum within the control volume with respect to time. That is what with respect to time. This is what is a momentum outflux from this control volume. This is the momentum change within the control volume. This is the what momentum outflux per unit control volume. These two can indicating for us two force component, one is body force, another is the surface force. That is what body force and the surface force component. So, if you look at that, what we are deriving this, that we are not bringing a new physics to that. The same concept we are talking about, that we know from Newton's second laws, the force is equal to mass into acceleration. The same concept we are talking about, but we are talking about a control volume. That is the difference. The control volume acted by at the surface as a surface tensors, as well as it has a body forces, which is the gravity components what we are considering it. So, if you look at these Jaeg's equations, if you have simple derivations, alternative form, okay, with more derivations you can just go through the derivations, go through the Singhal-Simbala book. I am not deriving one by one. If I look at that, just modify that, I will get this component, this is vector is equal to v dot del into v, that is what is equal to rho g factors del dot sigma I j. Okay. So, just the same Cauchy equations, if I just use the vectors relationship, I will get this part. As we discuss it, this is nothing as the local accelerations, this is what the convective accelerations. If you just split it, this is the local accelerations, this is the convective accelerations. That means, we can rho dv by dt is equal to rho g del into sigma I j. So, this is what mass, this is the mass into acceleration per unit volume, that is what is this dv by dt is accelerations into the rho, that means it is a showing it, if I divide by this volume, I will get this part, and the force what I have a body force, I have a surface force. So, if you look at that, even if you do a vector notations, we are deriving the very basic Newton's second law is that force is equal to mass into acceleration, nothing else. Please remember that we are not deriving a new hypothesis, we have followed the same hypothesis, is that force is equal to mass into accelerations. Here in the fluid flow, we have a body force, we have a surface force. The surface force we are considering from the stress tensors. The body force we have the g components, that is what we are getting a body force and surface force. Mass into accelerations, that is what we have the mass acceleration, but per unit the control volumes, that is what we are applying it to get it these equations. So, this is very easy, the same the great equations of Newton's second laws, the force is equal to mass into accelerations, only we have a change of the formats. Okay. For a control volumes, we are writing this form, which is having a two force components, the body force and the surface force component and the accelerations part. Okay. That is what we are deriving it. If I consider it, that same concept as that is not the difference between Cauchy equations or Newton's second laws, both are the same. The Newton's Cauchy's equations we are applying for the fluid of a control volume B, which is having a surface tensors, the gravity force component, we are doing that part where you know it how to apply the Newton's second law for a solid particles or solid motions, that you know it. That is what we are deriving for this. Now, if you consider it that I have these big control volumes, which is movable control volume, okay. It is moving it. The moving control volumes, which is having velocity v, which is having accelerations a, and we have the sum of the force components. So, it is a movable control volumes having the velocity v and also have the accelerations a. I can apply the same concept as if you look at the derivations part, is nothing else that force is equal to mass into accelerations, and the accelerations component I can write this, and followed by I can get it dx dy dj, nothing else is the volume of control volumes. Okay. So, if we consider a parallelified control volume, which is simple to derive the equations, not going for surface interval volume integrals, it is easy for us to do it. So, if you consider this type of simple control volumes, the Cauchy's equations help us to derive the simple form of equations vectorically you can remember it both way, that how the equations are there. Even if you have a doubt over these equations, okay, many of the times always we have a doubt about the equations, how it is there. Okay. That's the common things. Okay. When you have big equations, and always we put a doubt over that, how these equations are all the components of equations are correct or not correct. What I can suggest you, please look the dimensions. Okay. So, the basic equations what I have, rho dV by dt is equal to rho g del dot sigma j. Okay. What is the dimensions of this side? Rho is m by L q into accelerations, okay, L by t square. So, you can just cut it. Okay. You can see that this is what force per unit volume, that is what you will commit. Okay. That is what you can see, that this is a force per unit volume. Same way m by L q, g is a accelerations unit, you know it, L by t square plus what is the unit of this? 1 by L. Sigma stress is a force per unit area. So, force you have a m L by t square, unit area is L square. So, if you look it, just put the dimensions. Once you put the dimension, you can understand every part. The del is the dimension by 1 by x, that is what 1 by L is here. So, if you put the dimensions, you can see these are all the component force per unit volume, force per unit volume, force per unit volume. That is what this is. Force because of surface force, this is a force because of body force, this is the force because the body is moving with a velocity v, which is having the acceleration component is a. That is the basic things when you look at the basic equations of Cauchy's equations, if you derive from Newton's second law concept. Always you can tell it that if we can get directly from these simple control volumes with a movable control volume, what is necessary to derive Cauchy equations considering infinitely small control volume? What is necessary? The necessary is to demonstrate it that we are discussing the velocity field, we are discussing about density field, we are discussing about the pressure field. All this field we derive it for a small control volumes. The basic equations is this part, whether you can have a this just to demonstrate it that these are all the field. Okay. That is the reasons we have considered infinitely small control volume. Otherwise, I can use the same Newton's second law to derive directly these equations. No, we follow to show you the velocity, density, the pressure, the stress tensors, all are continuous functions. You apply through a control volumes using the Reynolds transport theorems and the Taylor series. We demonstrated that the functions what we are getting it, which is as close to as we are getting from simple derivations. So, basic idea you to demonstrate it, all this field, the velocity field, the density field, the pressure field, the trace fields, all are having a functional dependency of the space and time for a infinitely small control volumes. If I derive it with a Taylor series with a Reynolds transport theorems, the finally we will get this form of these equations, nothing else. Okay. That is the reasons I want to say that please do not be fear about the equations. Okay. Try to understand the physics, which is a very interesting, and that is what will make it force is equal to mass into accelerations, nothing else. The same we have the different formats. To demonstrate you that in a fluid flow, we have to consider these are continuum functions with a space and time, the trace, the velocity, density and the pressure, as I demonstrated in the first class itself. In fluid mechanics, what we look at? We just look at what will be the velocity field, what will be the pressure field, what will be the density field, what will be the acceleration field, what will be the trace field. All we need it. That is the reason we try to solve these equations. Okay. So, if you look at that, the same concept we are talking about, do not have a fear about vector notations of these equations, which is looks very difficult, but I do believe it. Today's what you have a computational efficiency as well as the materials what is available in many platforms. I think you can understand very easily all these vectors components. Okay. Let me I go to the next level, where I will be just telling it that many of the times I do not need 3 dimensionals the Cauchy equations. Okay. We are enough look at the 1 dimensional part, but always you can say that how do we can remember that equations, which is looks very difficult. It is not a difficult, it is a very easy equations to remember it. First what we can do it, always draw the axis. Okay. So, draw x, y, z. So, we have a friendliness. Whenever you solve the fluid mechanics problems, you draw the Cartesian coordinates or cylindrical coordinates or polar coordinate systems. The fluid mechanics problems, before solving, you have to scale the coordinates. Okay. That is the axis, that is what is necessary. Once you put the x, y, z, you can write the scalar component u, v and w. Okay. So, that is we know it. Okay. Then you can write other components, okay, which I am not looking now. I have to look at the stress component, which is acting to parallel to the x directions. Okay. So, I am to, so what I will do it first sigma x x. So, you can understand it, it is acting over this surface and perpendicular to that, which is one y x sigma z x, which is all threes are acting along the x directions. Okay. So, you can take the surface, you can look at that, this is a sigma y x, and take this surface, you can look at what is the sigma z x. That is what you can notate it whenever you sketch the figure coordinates. As soon as you put the coordinates, write u, v, w. Same way, if I am to write this part, okay, I will write sigma y y, okay. Sigma will be the x y, sigma z y. So, these type of notations you just have a practice, or you can easily find out that these are all in x directions components. So, I will putting the second subscripts in the x directions, then x y z. The same way I am putting it away, this is what over the y directions, I am putting it x y, y y, z y. So, I can put it in this way, the z direction. It is a very simple way, but please case the coordinates, write down the scalar components of velocity, then you write the stress components in each directions and try to understand it, which plane it works, which is the directions of acting of these stress components. Now, if you look at, if I draw this part, now these same Cauchy's equations, if I am to write in x moment, x directions, it is easy as I know it. So, my component will be du by dt, this is total derivative. Okay, I can put a capital D also, but okay. Rho g x, the g components which is commit here, we can put a g x. Okay. Do not have a confidence that it is act vertically downwards or u y x, that please do not consider that. The g can be a vector, so we will have a g x, g y, g z. So, this is a scalar component of the g, sigma by sigma x, rho x x, that is what is acting in the x direction, y rho y x, delta by delta z is rho z x. Okay. So, you can look it, if you just look at this part of the component, always you can write this part, it is not a difficult. The same way, if I write for the y directions, dv small v dt is rho g y delta by delta x, that is the components what I am looking at this way, sigma x y del by del y, sigma y y del by del z, sigma z y. So, same way you can write for the z components. Most of the fluid mechanics, when we talk about the spacecraft, we talk about biological science, we cannot make it the y axis verticals, because we have to simplify the fluid mechanics problem. So, that times it is very easy for us to make a gravity force component in 3 directions, x, y and z directions, then solve the problems. That is the reasons many of the advanced fluid mechanics books, they follow the gravity components having the g x, g y, g z, that is the difference. Now, let me go for the next part, which is Navier-Stokes equations. Okay. What the Navier-Stokes equations did it, and what is the problems was there from Cauchy's equations. The problems or the mathematical challenges. Okay. If you look at this, the equations what we have in Cauchy's equations, we have a stress tensors, okay, which is having 9 components. As look at the stress tensors is having 9 component. Even if you look at symmetric cases, so it comes back to a 6 components. Okay. So, if you 6 are unknowns are there, then we have a unknown functions, we have a density, we also unknown having the velocity scalar component. So, that means we have a 10 unknowns for 4 equations. Okay. So, 3 equations from Cauchy's equations, 1 equations from mass conservations. How can I solve the 10 unknowns for 4 equations? We need to have the approximations here. The Navier-Stokes equations does that approximations, that to reduce these unknowns, the 10 unknowns to the 4 unknowns, so that with help of the 4 equations we can solve the problems, because we have 3 equations from Cauchy's and 1 equations from mass conservation equations. So, we have 4 equations, 4 basic governing equations with us, but at present we have trace components are 9 components, but if you consider the symmetric, then even if the symmetric cases I have 6 components, 6 plus 1 is density and the velocity is 3 scalar components. So, that way I have 10 unknowns for the 4 equations. So, basic idea comes from the Navier-Stokes equations, okay, which looks like that almost 40 to 50 years works to reduce this the equations which is in a 10 dependent variables. Okay. 10 dependent variable equations can make it to a reduce the variables, okay, dependent variables from 10 to 4. So, that we can solve it with certain assumptions. There is no doubt about that. Since it is a very basic level of the fluid mechanics, I am not going to advanced level. Those are interested for the advanced fluid mechanics level, they can have a advanced fluid mechanics course, or there are the lot of books are there and you can follow it. So, the basically our objective is here to reduce the dependent variables which is the 10 dependent variable to the 4 dependent variables and the 4 equations, and we can solve the problems. That is the idea for Navier-Stokes equations. First approximations what they have do it is very interestingly they consider it that if you assume it the fluid at the rest, if you are assuming the fluid at the rest, at that point there will be no shear stress, that is what you know it. So, there will be no, that is what the shear stress components becomes 0. Only what we will have through the Pascal's laws, that I will have the pressures which is the equal amount of the pressures will be acting in all the directions. That is what I will get it when you have a fluid at the rest. That means, if I consider fluid at the rest, my stress tensors which I defined earlier, that comes out to be, again I am just writing for you the stress tensors what we are define it, that is what will be becomes minus P 0 0 0 minus P 0 0 0 minus P, that is what will become it, because there is no shear stress component when fluid at the rest. That is what the basic definitions of the fluid at the rest condition. When the shear stress 0, as equivalent the stress tensors will be a functions of the pressure. The negative sign we have considered, as if you look at the stress and the P is a opposite directions, that is the reasons we have used the minus P component. That is what the basic concept has started it, that we can split the stress component into 2 components. One is having the pressure and another is having the shear stress component. That means, if fluid start moving it from rest to a moving conditions, then the pressures component what will be built up, that is what will come out to be this. So, it will have a 2 components. It will have the 2 component, one will be the pressure functions as similar it remains at the rest. Okay. As it is moving it, this is what you have a viscous stress tensors. Okay. That is what the viscous stress tensors what we will get it, which will have a same notations. If you just look it, if are like stress tensors, it is also easy to write it. Okay. Do not be have a confusions much. Sigma xx, first you write it. Okay. Next will be in the same x directions, it will act it, but the plane which is perpendicular to the y axis, then z axis. So, this is what all x direction. So, same way you put it for y directions, that is what will come it x and y, this will be sigma y y, this is what will come it z y. So, you remember it, the second subscripts will be the same, it will move x y z x y z. So, same way I can write it for this is y direction, this is for z direction. Sigma x z sigma y z sigma z. So, please have always have a practice to write this component, the subscript form components, and this is the x direction, this is the y direction, this is the z directions. So, this is in the x directions, second subscript will be the x. So, as going from up to down x y z, x y z, x y z, that is all. So, if you can remember these notations, which is not difficult, always you can remember these notations, because that is what, and always thinks that this is a stress acting on this surface. That is what you have to visualize. This is the trace components acting over the surface. The surface which is a parallelepiped, or very simple way you can understand is a cube. Over that cube surface, I have a internal resistance force per unit area. That is the, and here the viscous components plays the role. So, very technical way we divide the stress components into, for a moving fluid, in two components. One is the pressure components and another is viscous stress tensor or divertidic stress tensors. More details I am not going it, because you can look at detailed derivations of any advanced fluid mechanics book, but try to look at the Navier-Stokes equations, try to separate the fluid stress into two components, one component for the pressure, one component which they get it, they define is that because of internal resistance, which is the stress component because of viscous components. So, more details I am not going through it, but if you are interested, always you can look at advanced fluid mechanics book. Now, for just to revise it, the basic things what we discussed lot in very beginning classes about Newtonian fluids and non-Newtonian fluids. Okay. As Newtonian fluid. So, this is what is established the relations between the shear stress, okay, stress tensors and strain rate tensor, or Newton's laws of viscosity established between the shear stress and the shear strain rate. That is what you know it. The tau is equal to mu dV by dy. That is what the Newton's laws of viscosity, and mu, as you know it, it is a dynamic viscosities. So, if you look at that the same way, we can always put a relationship between sigma, the stress, and the strain. Again I am hyperbolizing strain rate. Okay, that is the reasons, basic difference between the fluid mechanics and the solid mechanics. As you know it, it has a relationship between stress and strain in the fluid solid mechanics, but in fluid mechanics we talk about strain rate, the change of the strain with respect to time. Okay. So, this relationship, if it is a linear relationship, okay, having a direct relationship like most of the normal fluid, okay, with air, waters and all, it follows basic relationship between stress and tension, linear relationship. That what makes us a validity of Newton's laws of viscosity, as well as that fluid flow we define as Newtonian fluids. In this course we will talk about Newtonian fluids, but today's world we have a lot of the flow does not follow this Newtonian fluid concept. For examples, if you talk about blood, okay, biomedicals, okay, you talk about even if slurries, you talk about the suspensors, the polymer solutions, they do not follow a linear relations between stress tensors and the strain rate sensors. Okay, that is the reasons. Mostly we are combining it with air, waters, the kerosene and gasoline. So, please have a knowledge over that. The Newtonian fluids, the Navier-Stokes equations is what derived for the Newtonian fluids, that cannot be used for non-Newtonian fluids. We need to do a lot of other things, but let not be discuss this. This is what the Newtonian fluid flow is defined by this, what is the relationship between shear stress and shear strain rate. That is what is the Newton's laws of viscosity. Same way we can have the relationship with the stress and strain rate. That relationship all give us the Newtonian fluids. Before going to the next levels, I just to show you, we discussed that in chapter 17 on fluid kinematics. This is what repeating that we will have a many times we will have the fluids, we will have a subjected to the shear stress and it will go for rotations. Okay. That is a shear strain rate. Okay. So, now what is our idea is that if I can write the shear stress components, viscous shear stress component in terms of velocity field, that is what we are trying to look at, that can we write the shear stress components in terms of a functions of velocity components. Okay. That is the basic idea to derive in Navier-Stokes equations. What we try to look at, go back to the chapter lecture 17, where we discuss about a fluid element subject to shear strain, the linear strain, all we derive the equations. I am not going more details, as already we discussed in lecture 17. What we got it, that is what I am highlighting, that the strain rate sensors in Cartesian coordinates, we get it as a functions of u, v, w. No doubt this is a partial derivative components are there. So, we can get it these derivations, and these derivations already we derive it if you look at the fluid kinematics part. Okay. That is I am not repeatedly derive it, but that is what is giving me the strain rate tensor is a functions of a partial derivative functions of the scalar velocity of u, v, w. That is what we derive it. You can see this the relationship between them. Okay. Now, if you go for the next one, which is very easy for us now, because what we are looking at, we first look at certain assumptions. Okay. First is incompressible flow. Okay. That means density more or less fairly, okay, does not change with space as well as time. That means it is a constant. It is a constant. That is the flow is called incompressible flow. Next is that isothermal, okay, as flow. So, thermal means you can indicate it is a temperatures. Okay. Isothermal means within the fluid domain temperatures remain more or less constant. That means within the fluid domain we are not considering it that there is a temperature change. Okay. That is what a significant order of change of the temperatures. So, that is what is isothermals. Because the temperature does not change it, the dynamic viscosity is more or less is a constant. Okay. That is what it happens as the temperatures remains constant. We are considering a fluid domains where we solve it, we consider that temperature does not change significantly. Okay. In the fluid domains which we are considering to solve the problems. That means the dynamic viscosity that also remains more or less constant value. If I have these two assumptions, okay, this great simplifications of fluid flow problems. Okay. So, if you look at that and go through very detailed book is there, but it is quite higher level book, okay, of fluid mechanics by Kundu, Kochen and Dolling, which is really is a higher level book of fluid mechanics. If you go to it, they have established for the stress is a functions of 2 times of mu of sigma is del the stress tensor rate tensor. Okay. So, with these assumptions and the derivations which is available, as you can get it a relationship between it. The two factors always you can look at why it is there. I am not going details for that. So, if you look at that, I will getting the stress factors now in terms of the gradient of the scalar components of u v w. So, that is the advantage of this, that viscous shear stress we have written it for incompressibles isothermal flow with a certain assumptions with relationship between stress and strain rate. We derive it the functional relationship as a shear stress is this, as well as the stress tensor is like this. So, more the derivations you can do by steps, which is there in Simbala book, also you can see in FM White book, but basically it is a relationship what we have derived from fluid kinematics with certain assumption is as the incompressible isothermals. We are deriving the relationship between stress tensors and the strain rate tensor, as the strain rate tensor is a functions of the gradient of scalar u v w. That is what the advantage we have. If I have this, if I use this relationship in the basic Cauchy equations, then I am just expanding. This is what the pressure components. Okay. If you look at this is what pressure, this is what gravity force component. These terms is because of viscous stress components. So, if you look at that, you just substituting that, you will getting all these viscous stress components, which are the functions of mu and u and v w. Okay. Mu, u, v w. That is what is the in the x directions. That is what is the in the x directions. You can derive similar way for y directions and the z directions. Now, if you look at that is what is the derivations what is given it here, that the pressure is a normal stresses only. Okay, that is what is this, and viscous stress tends consider both normal and shear stress component. It contributes the three terms. If you look at there are certain assumptions which I am not going details, like if you look at this the functions of when you have do the two differentiations, okay, x or z or x z, that reverse things does not matter it, as it is a smooth functions of x, y, z. You can equate, they both are the same values. If I consider that, rearranging these terms, I get very interesting equations. Okay. This is if you look at this is a continuity equations. Okay. Del dot v is 0 for incompressible flow. That is what, if I substitute that values. Okay. Now, what I am getting it, again I am just to rewrite it, because we retain these things, the accelerations components. Okay, this is a total derivative minus dp by dx. So, new terms has come because of pressure gradient. This is the force component because of pressure gradient, rho g x, then we are getting it mu times of Laplace operator of u. Okay. So, that is the mu is a constant for us, as we consider is isothermal case. So, we are getting it the additional two components, which is a shear stress component, the stress components were there, we split into two parts. One part is pressure components, which is we getting a pressure gradient component here. We also getting it the components because of viscosity is that mu rho square Laplacian operator of u. If mu is equal to 0, so you can easily say that this is equal to 0. That means your basic equations is du by dt is del p by del x rho g x, which is a form of Euler equations. There is nothing else. It is a, if there is no viscosity components, we can reduce to a Euler equations. If we consider the fluid at rest, so u is equal to 0, dp by dx, okay, plus rho g x is equal to 0, which is the equation for hydrostatics. So, if you look at that, the equations what we have derived the Newton Navier-Stokes equations, if we simplified it, we will get it in different forms, Euler, or we can get it basic hydrostatic equations. So, we need to remember, not to remember, it is okay, I can say it, you know it mass into accelerations in the scalar directions of u x, x directions I have a u component, that what total derivative will be a force due to the pressures gradient because of change of the pressures, okay, that is the pressure gradients will give a force to that, the force due to the gravity, force due to this the viscosity, that is what we can simplify it as a mu times of Laplacian operator of u. That is what is very interesting. And if you look it for other directions, I think we can derive it for y directions and z directions. As I just emphasize is that you just look at the notations, okay. Here g x, g y, g z, this is gradient in x directions, the equations what we are deriving for this is a gradient in y way, so gradient in z directions, showing that what is the pressure force is acting on, okay, per unit volume. This is the gravity force component, and this is the three force components is coming it for us as a Laplacian operators of scalar field of u, v, w, representing us viscous terms. Okay. So, now if you look at these equations which we derived now as the basic equations, what I derive it as the Navier-Stokes equations. This is the three equations what I have. The Navier-Stokes equations gives me three equations, as you can look at that these three equations we are getting it, plus we have a one equations is a mass conservation equations. But these equations, if you remember it, it is the equations what we have derived for the incompressibles isothermal cases. Okay, that the assumptions you have to look at. For that derivations, we have a three equations what we got it, which is a nonlinear second order partial differential equations. One equations we have from the mass conservations. So, that means again we have a four equations, no doubt about that. But if I just look at how many dependent variables now, okay, how many the number of dependent variable, if you look at as this flow is incompressible. So, density is not there, it is a constant value. I have a three velocity components are unknown and I have pressure components unknown. So, Navier-Stokes has made it us very simplified it with certain assumptions, no doubt about that. We make it the equations with a 4 equations, 4 dependent variables, 4 unknowns to be get it, which is a function of space and time, which is the scalar velocity components u, v, w and the pressure. So, we have 4 equations and 4 unknowns. So, we can solve it, but still it has the problems is comes it here is it's a unsteady time component is there, non-linear partial differential equations. So, we may not have a exact solutions, okay, unless otherwise very simplified case, okay, unless otherwise we need to do a lot of approximations to solve these equations, because still it is a 4 equations and the 4 dependent variables. Density is not there because flow is incompressible. So, if you look at that, you have a 3 u v w and the pressures, that is what 4 unknowns for me, 4 dependent variables. So, I have to derive it from the space and time. That is my solutions for a particular fluid flow problems by solving these 4 equations. The problem is it is unsteady, there is a time component, the equations are nonlinear second order partial differential equation. If you look at this is a second order. So, that is the reasons we work for approximate solutions. That is the reasons we discussed from very beginning it that we look at the fluid mechanics problems, still it is in this century is a challenging task for this million era problems, still we have not solved it. That is the reasons we try to look for a approximate solutions, because there is no exact solutions, we will get it unless otherwise very simplified cases like plate movements moving of 2 cylinders, where this is a simplified cases we can get the some solutions, analytical solutions, but we cannot get a exact solutions of these 4 equations, which is the 4 dependent variables, because it is a nonlinear partial second order partial differential equations. This nonlinear things makes us very difficult to get a exact solutions. That is the reason we look for a last almost 50 years we are looking for approximate solutions of Navier-Stokes equations in different forms. That what is given birth of computational fluid dynamics, which we discussed many times. So, this is the reasons we have the CFD now, because there is no analytical solution, otherwise there were no CFD or no computational fluid dynamics in subject of anybody, because if you have a exact solutions of Navier-Stokes equations, even if for incompressible isothermal cases. With this I think today I will just to make it this part to show you it is a big form of equations, okay. Always you expand it, it looks very difficult equations, but please try to understand it is nothing else, is a mass conservation equations del dot V, that is what easily you can remember it for incompressible flow. This component, as I try to explaining it step by step, always you can expand it, the local accelerations, the convective accelerations component, local and convective, the pressure force, the gravity force and the Laplace operator of u, v, w and mu times. So, the equations when you expand from the vector form, it looks very complex. As I said, it is a nonlinear second order partial differential equations, what we are getting it, that will be there. But many of the times we go for cylindrical coordinates, which is easy to solve it. I am not going derivations of the cylindrical coordinates, just show the this is what the mass conservation equations for the cylindrical coordinates. We discussed about this of how we will define this coordinate axis for the cylindrical coordinates, and one of the equations components looks like this. Okay, if you look it, it's really complex, as equation looks like that. Okay, and it makes a fairness, but I do not think it is that. If you really look at the same way the convective acceleration and local accelerations, and look at the Laplacian operators in the cylindrical coordinate systems, you will get the same components what we will be talking about that. So, more details if you look at the theta component and z components. Okay, these equations are more complex. All these equations are available in Shenzhen Chimbala, even if FM white books. Okay, I am not encouraging you to remember these equations as it expected, not expected in many problems. Okay, I do believe it. Look at positive way these equations what we have derived from Cartesian coordinates. Try to understand in vector forms. It is easy to interpret it at the vector form as compared. Look at each components as in a cylindrical components. So, in the next class we will talk about what are the boundary conditions and some of the basic features of the Navier-Stokes equation, as well as we will try to solve few of the problems. Thank you.